Zurück aus der Pause, nach dem Apero. Alle wieder da. Wir starten sofort im zweiten Teil von der Datacenter at Night, 19. September 2013. NUTANIX, Rechenzentrum der nächsten Generation.
All right, guys. So maybe we'll just start. Like Frank had said before, please interrupt, ask questions. It'll make it very interesting for me and for everybody around. So just don't hesitate. There are no stupid questions. Quick intro about myself. My name is Karthik Ranganathan. I'm a member of the technical staff at NUTANIX. And I used to work at Facebook before this for about 6 years. I worked on a lot of big data, data-intense technologies like HBase and Cassandra over the last 6 years at Facebook. And I'm going to tell you guys like roughly about how the data center and the architecture is done at Facebook to handle the scale, and then tell you how that kind of applies the same philosophy, the principles apply to what NUTANIX does, and we can go forward from there. Okay? This is the rough agenda, the way the slides flow. So quickly going to talk to you guys about how data is stored at Facebook and how it's organized, and then going to drill down specifically on one of the storage technologies among the many that we use. It's one of the large storage technologies that we use. It's called HBase, and it's used for both online transaction processing, OLTP, and analytics, which is the warehouse style. Right? And then we're going to talk about some general principles that we've learned about operating at scale, and finally give you guys a comparison of what these principles are that we use at Facebook and how NUTANIX compares with them. So let's get started. Big data, right? By big data, I mean a lot of data. How do we organize our lot of data at Facebook, right? I kind of thought through and finally categorized them into 3 buckets. The first one is user databases, which is if you try to log into Facebook and see your news feed, all of that stuff is stored in a MySQL database. Now, there's a lot of these MySQL databases running on a ton of machines, and so orchestrating this, making sure that things are still up and running on failures, provisioning new machines, that's the challenge, right? And that is one of our big data stores. The next one is about photo uploads. There's like hundreds of millions of photos flowing into Facebook every day. So, you know, yeah, a lot, right? So we started out with a NetApp-like solution, but pretty quickly realized that it's not going to really scale, like cost-wise or performance-wise, because in aggregate, we have billions of photos, but only a few of these photos are accessed or hot at any time, and what really matters is actually the dollar per gigabyte, how much it costs to store the data. So we built a custom solution, and that's called Haystack. And this for both photos and videos. Now, third is where we store our Facebook messages. So all of the messages data that flow across between people on Facebook, and also a lot of other sundry use cases like the operational data store, search indexing, and so on and so forth. And I'm going to give you guys an overview of all of those, and we store that on top of HBase, right? And we'll get into what HBase is right on the next slide, so bear with me here. The next kind of use case is the non-online use case, but yet very, very business critical, the analytics piece or the warehouse. This is used to derive relationships and intelligence from all the data that we can collect and use that to enhance our service to the users, the business, the what have you, right? And for that, we have Hive, which is also a system which was grown and developed inside Facebook. What Hive is a SQL-like simple query interface. You can submit a query to it, and the system will actually generate a ton of MapReduce jobs and do whatever it has to go through a lot of data and summarize the results for you. And the data that it lives underneath is usually semi-structured, and a lot of it keeps flowing in. And graph search indexing. So there's a graph search that's there in Facebook where you can ask questions like, show me all photos of me that were liked by my friends, or stuff like that, really complicated queries. And for that, we need to build indices so that you can actually serve this data. And that also, the indexing for that also falls into the warehouse case. And we're going to look at that in more detail. So moving forward, what is HBase, right? HBase is it's an open source project, and it's a database which is modeled after big tables. I mean, Google's big table, right? And what is big table? So HBase is a large-scale distributed data store, right? And Google has GFS, which is a large-scale distributed data store which stores large sequential reads and writes. It's good at handling large sequential reads and writes. The open source counterpart to the Google file system, or GFS, is HDFS, or the Hadoop distributed file system. Now, to make random reads and writes efficient on top of this sort of a large read and write system, Google built Bigtable, and the open source equivalent is HBase. Okay, so HBase runs on top of HDFS, or the Hadoop distributed file system, and is really efficient at random reads and writes. So let's get started about why HBase, how the whole thing started. It all started with Facebook messages, right? So at Facebook, you can connect with a person, and you don't really need to know how you're connected with that person. You just know you're connected with that person, and you can find that person and interact with them. So then, at this point, we thought that, and at this point, you could send a message to that person by sending him a Facebook message, which is internal to Facebook. You can send an email to that person. You can send a chat message to that person. There are many mediums of communication. And the thought was, why should you have to know how to send this? Because, like, for example, my really young cousin will never ever check email, but she'll check chat, so I'll send her a chat. But my uncle, oh hell no, he's not going to look at chat ever, so I got to send him an email. I don't really need to make this decision, right? Because the network can do that better. My uncle knows what he reads better than what I do, right? So the aim was, let's just unify all these means of communication. Let's not worry about, should I chat, should I send a message? Just do it, just send something, and we'll deliver it the right way. So that was the vision. And what did that mean for somebody that's working in storage? It meant a lot of data. So there's messages, and then there's chat, right? There was only chat in the memory that was being stored until then, and now that meant every single chat, every email, every message, and every SMS has the same first-class citizenship in this storage system. So everything has to be written before it is acknowledged. Irrespective of whether you think email can be slow or chat has to be really fast, it has to be written. So a lot of messages. Okay, how did we pick HBase? We evaluated a bunch of storage options. We looked at MySQL. We looked at Cassandra, which was built inside Facebook for purposes of storage, inbox search, so just the search data. And then we even looked at building a custom storage system, and we looked at HBase and a few other options. Now, here are some principles that we came up with that really, really became important. It became very obvious very quickly that these are very important. First is horizontal scalability. What that means is, when you're having billions of messages flow in, you can't really provision for the next 15 years because your hardware is going to depreciate. You're not going to be able to utilize the more modern, more efficient hardware. You're only going to provision for a little bit into the future and add as you go. So the act of adding machines, or horizontal scalability, not vertical, because you can't read all the data out of a really, really dense storage machine and then put it on another, and that would just be impossible to manage. So the act of adding more machines should be extremely easy, right? The second point is automatic failover and load balancing. And there's two parts to this, and we'll go over both. So when a machine dies, so now that you're able to add a lot of machines, now you have a lot of machines, right? Now when you have a lot of machines, machines fail, because that's what they do. And you can get enterprise-grade machines, great. They're going to fail a little less, but when you have enough of them, they're going to fail. So failure is the norm, right? That's what happens. So when a machine fails, if you have to wake somebody up and that guy has to come and quickly do something and then do some more magic, and then you got to get it up and working, it's hard. At 3 a.m. it's much harder because you're. So in the weekend at 3 a.m., man, it's even harder. So you want it to automatically work. When a machine fails, you want another to take its spot, right? That's the general principle. So you don't care about machines failing. I'll come back after the weekend. I'll have my good sleep, come back, and then fix the machine when I know what I'm doing, right? So if a single other machine takes its spot, right? This is the other key part. When one machine fails, if one other machine takes its spot, that's no good, because if the original machine had failed due to too much load, the next machine is going to fail due to too much load, and the next one after it, and then like a sniper, you're going to have all your army of machines shot down one by one, and you're not working, and you're up again at 3 a.m. doing the stuff you don't want to do, right? So what you want is really load balancing. You want a machine failure to be picked up by a bunch of machines so that the load distributes, and you're not into this situation where every other machine falls out like a domino, right? So that's the second piece. So automatic failover, and load balancing. The next piece was optimize it for write-heavy workloads. Now, all of the large data use cases don't usually read everything that they write, because then they won't be big. I mean, it won't be as big an amount of data. So you got to optimize it for being write-heavy, a lot more writes than the number of reads. The reads will be here and there. It could come at any point and ask any piece of information, but it won't read everything it writes usually. So make it optimized for write-heavy workloads. Now, we had the additional advantage of HDFS, the Hadoop distributed file system, being extremely battle-tested at Facebook, because we had a petabyte scale warehouse cluster already running and answering business questions. So we had a team that had a lot of expertise, engineering expertise, DevOps expertise on keeping the cluster up and running, making changes and feature enhancements and requests, and so on and so forth. We knew failure patterns. We knew how to provision new machines, how to install the software, everything, right? So that was a big plus for us. And last but not least, we didn't just want to do this whole thing for messages. We wanted to make a generic store that could be leveraged across a lot of use cases. So we wanted a strong consistency model. Now, Cassandra, that I mentioned before, is also built in Facebook, but it's built on principles of eventual consistency for a different use case, right? Which was for a read light, very light, and write extremely heavy use case, and where eventual consistency is acceptable at the application level. But here we wanted something which is strong, because if you're putting a cache in front of a store, the cache is going to read data from the store and cache a value. But if the store heals underneath and changes the value because it's eventually consistent, you're now going to have an inconsistency. The cache will serve something. When the cache value expires, you're going to read and cache yet a different value. So what you read will change at different points of time, and that's a little harder to program against. So we decided to go with something that's strongly consistent. Now, let's move forward. 2-year-old stats, almost, right? This is 2011. Still going with that. The traffic to HBase, because of the messages product after we released it, was in the billions of messages, like tens of billions of messages per day. That's what flowed into our system. We had about 75 billion RPC calls, like the number of calls that was called from the upper layer. The upper layer was a dedicated write-through cache, an application layer, which was a write-through cache for messages. It was a smart layer that knew when to cache messages and when to throw them down just to storage, based on when the user was whether the user was interacting or not. And that sent about 75 billion writes to the store underneath. The usage pattern was about 55% reads and 45% writes, after a lot of reads were actually filtered out by the write-through cache. Now, your average write, so you had 75 billion RPCs, of which 45% of which were writes. And each write, on average, touched about 16 different records. Now, why 16? It's because we computed the search index inline. We computed the actual message, the metadata, the threading model, everything, and we wrote everything together in one shot. So it would actually go and affect 16 different records on average. So, and these numbers are a lot larger now, by the way. So this is 2 years old. Data sizes, again, 2 years old, but we had over 7 petabytes of online data, which means there's 7 petabytes of data, and you would be asked to serve anything at any point. Any byte of them could be addressed at any point. And that's without replication. The size of clusters we ran required, per our calculations, a 3-way replication to minimize the probability of loss, to make sure that we never lose data. So that turned out to be 21 petabytes on disk after the 3-way replication, and that's all LZO compressed. So that's all compressed data. And this did not include the backups we had on our live and serving cluster, because somebody may code at 3 a.m. and they may make a bug, push it into the software, data is corrupt. Oh man, can we go back to how the data was yesterday? So you needed to do that quickly. So we had backups on the live serving cluster, and this 21 petabytes does not include that. Now the growth rate, 0.5 petabyte a month. So that's the rate at which we grew, which means that every year we would need almost 20 petabytes of raw disk just to sustain our growth rate. And the growth rate goes up, by the way. It's not really static. It never goes down. Don't ask me why. All right, so 10 petabytes is not 10 times 1 petabyte. It's not that simple when you're trying to make the thing work. It doesn't scale that easily, right? There's a lot of features that need to come in order to make sure that the system is still functioning efficiently with larger and larger amounts of data. So we constantly had a need to innovate and find newer features and find bottlenecks and eliminate them and so on and so forth. So in the read and write path alone, we had put in a ton of improvements, performance improvements, IOPS reduction so that you seek less and you read less and you can serve the thing faster. And also we had to rewrite the entire database file format because the metadata was being paged in at too coarse a level, and if the metadata that was a large chunk of metadata that was read, if it got paged out, would be really, really slow to get paged back in, and we had to make sure that the metadata was also finely chopped up and so on and so forth. So a lot of changes to make sure that you were just able to support that density of data per node. And then it's not just about the performance on a box, it's also about how do you not clog your network trying to read so much data, right? I was having a very interesting conversation with someone like just a little bit before, and that was one of the big things we had to invest in, which was trying to make sure that your replicas are placed in such a way your failover does not happen to some random node which starts pulling a lot of data over the network, because it wouldn't be able to pull as much. Once your data density goes above a certain amount, you try not to move the data to where the compute is, you try to move the compute to where the data is, because your network has to scale a lot if you did it the other way. So we had to make sure that the replicas were placed in such a way that once a node failed, you fail over to a bunch of nodes which are not random nodes, but which are nodes which have all the data that they want. So that means you have to do a shard level block placement. So a node has a bunch of shards, and the shard level block placement is done on replicas so that when the node fails, the shards can go to a bunch of other nodes, not just any one node. And so that act of sending the shards to the right node which has locality is what we call locality-based load balancing. So we had to bring in a concept of don't just send it to the guy with the lowest CPU, because he's going to pull everything over the network and bring everybody down. Send him to the guy who has all the data and the lowest CPU. So it's a little more complicated, the load balancing, right? So now that was all about messages. And there are a few other online use cases of HBase. The first two, the operational data store and the multi-tenant key value store, I will go into in a little bit of detail, so I'm skipping that right here. But the site integrity is about monitoring certain basic actions of users, like how many friend requests do they send, how many messages do they send, or what have you, to make sure that the site is spam-free and has high quality so that people actually enjoy the experience on Facebook. And we used HBase to store data and analyze, and we used to find about tens of thousands of fake accounts per day, spammy users per day, and shut them down. So another use case for this general purpose store. Now, that was the online part. On the warehouse part, there was the whole graph search engine, that the indexing for which was done on top of HBase. So I'm going to go over that also in detail in a little bit. So I'm skipping that for now. But the second piece was the Hive use case, where we had to put HBase underneath Hive. Hive, like I told you, is the analytics engine where you can submit a simple SQL-like query and it'll give you back your response, but underneath does a lot of coordination and circus to get you all your data, analyze it, and give you back the consolidated result. Now, the actual sheer amount of data, so the way, how does this work, right? Like, let me maybe go into that real quick. So you keep getting data all day long. After midnight, you say, oh, day done. All right, let me start ingesting that data, process it, and put it into the data store. And then the next day, when people come to work and want to run some queries, it's all ready to go. Except the rate at which data grew was so large, and the daily data rate was so big, the amount of data we collected through the day, that it would take us more than 12 hours to actually process that data. So, you know, if the data is not ready when you come to work, unless you come to work really late, so, you know, so, and so we had to come up with a different way, and people were like, man, what's this stuff? What are you guys doing? You know, and so on and so forth. So we had to come up with a more real-time way, because 24 hours it's idle, and then you want to process the whole thing. It doesn't work that way. So we decided we're going to keep processing it all the time. And there was also a need for real-time analytics. Why are you giving me this day-old data? Could you give me data that's a few minutes old? So, you know, that was the other use case. So we had to use HBase underneath Hive for that. And it's really suited to this sort of an application, because once again, it's really easy to scale and it's write dominated. So those are the the key things. Okay, so now we'll go into some other use cases of HBase, like the ones that I skipped over and I promised I'd come to. So the operational data store. By the way, if you guys have questions, feel free, right? Still remember that. Okay, operational data store. What is it? We collect data from a lot of machines, right? Data flows in from all the machines, which talks about its own health. How good are my disks? What is the CPU? What is the user CPU, system CPU, the memory used, whatever, what have you, everything, right? And there are applications running on machines, and the owners of these applications also want insights. So what is the number of queries I'm serving, my latency, the number of queries I'm sending to the layer below, and then there's switch. How much data am I sending up, down, whatever, right? And then the node level, the NIC, how much of bandwidth am I using on a NIC? How much is it across the rack? So there's a lot of metrics, right? This is a long story short. So we collect all of those metrics, and all of that flowed into the store, which was HBase. And the metrics were collected pretty frequently, like every 4 minutes, every minute. So it was pretty frequent. And all of them got stored in HBase, right? And when the user requested, there was a custom application tier which would crunch data, which would make sure the roll-ups are done, so on and so forth, and give people answers to how is my cluster doing, and aggregate them across a cluster level, aggregate them across node level, give you the 5 worst, the 5 best, give me the worst 5 disks that are performing in my cluster of 100 nodes. You could get that answer. So things like that. So it supported complex transformations, right? You could do, show me how the last 2 weeks, the 2 week over 2 week comparison, how did it perform? Or, hey, I know I restarted that machine and there are big spikes, but chop off those spikes, show me the rest of the graph. So you could do really, really fancy things with it, and it was really useful for us. And it had a really well-designed UI. So Facebook has a really good UI, and people in Facebook are used to that. They're spoiled by it. If the UI is not good, nobody's going to use it. So that's the way it is. So it had a really good UI, fortunately for the people, so everybody used it. Now, a couple of very interesting points here. Everybody wants to put more and more metrics into the metric system. At some point, it's really not worth saying, hey, man, you're putting like, do you really need those 5 metrics you just put in, or are you just like wasting my space? It's not going to work. You just let people put the stuff in. So what do we do from our side? Just add a few more machines and forget about it. So the architecture really has to be like that, because people want more machines, more applications, more metrics. Who are we to ask? So go for it. And the other part is, this system was also used for alerting. So once you have a lot of machines, you're not going to be able to figure out, hey, that machine is performing slow, or this is a bottleneck, or that. You want the system to tell you, hey, something's going wrong. You might want to take a look at this stuff. So we could set alerts which said, if a certain graph went above a threshold, below a threshold, stayed between a threshold for some length of time, then send me an SMS, an email, or whatever, and somebody could act on it. So this was our way of actually responding to any sort of fires, smoke, whatever on the site. So that's the way we did it. So, and that was a really, really useful UI. In fact, to such an extreme that even if on the engineering side, if somebody claimed they had really like turned the world, boiled the ocean, and made a 10x improvement on something, you had to show it on this graph. Otherwise, it didn't mean anything. So this was really, really useful tool. Okay, so quick stats about this use case. We had 150 billion operations per day on the HBase cluster just due to metrics. So that's what was happening. The usage pattern was very heavily read recent data. Everybody wants to know, like, round about when the issue happened, what happened, and that would mean like about roughly for the last day, everybody would always be asking for the data. So we had made special tuning into the database to make sure that those requests are really efficient, and that's really easy in an LSM style, right optimized store. So that was one. The second one was, we didn't want to store this minute or 4 minutely data forever and ever, because if somebody asked, show me the trend over the last 5 years, we didn't want to read all that data out and compute. So we would downsample. We would actually make sure that the 4 minute would become an hour, or like a couple of points per day, and make sure we do the roll-up so that we can serve the answers quicker. And the last feature, which was actually supported inside HBase, was you could tell that, hey, I want this data around for 90 days, and after that, just throw it away. So we would make sure that the new data and the old data don't mix. We keep the old data old and the new data new in the database layer, so that if a data file actually got older than your time to live TTL value, we just delete it. And so we didn't have to read the data out to purge. We could just purge it by just deleting a file. So it was easy. Next use case, Facebook Insights. What is it? There's a lot of people with a lot of websites, right? And admins want to know, I put my widget on the site, I put a Facebook like button, I put a comment button. Is it really doing any good out there? Is it like people are really doing anything with this stuff? So what we want to give is how many people viewed it, how many clicked on it. Okay, they clicked on it. How many viewed the newsfeed that went out? How many shared that newsfeed? How many came back to your site because of this? So complete the entire loop. And all of this cool stuff was being given to the admin. And on the HBase side, what did we see? We saw billions of URLs and millions of increments. So everything flowing into the system. But it didn't just, so this system was also a very scalable system. We had a lot of URLs, so data constantly flowing in. We could add nodes very easily to scale out the storage, scale out for sheer number of connections being made to the machine. So we could scale out on any dimension we want just by adding machines. And it could track a lot of different metrics inside those top level rollups. It could tell you like what are the number of likes, the clicks, the shares, the so on. It could tell you like how many people actually came back as a total, or what is the gender, the age group of the people, the location from which they did it, and whatever, a ton of stuff, right? And that keeps increasing over time, and you have to be able to accommodate everything. So, okay, so another use case, and I thought this one would be interesting because it's a multi-tenancy use case that we did inside Facebook. This was a multi-tenant solution on top of HBase where each and every application that was using it did not need the entire storage set or the entire or a dedicated cluster. And there were too many of them, so if we actually did put a cluster for each one of them, then there would have been very unhappy people trying to maintain that cluster and keep it up and running, because they would all be small clusters, but there would just be so many of them. So we decided, for sanity, let's collapse everything into a single cluster or a few clusters. And the next issue was that we had to educate everybody on how to use HBase. Hey, there's a column family and there's a write-dominated store. No, you can't put that stuff. Yes, you can put that stuff. So that quickly got out of hand. So we decided, let's make this thing simple. Let's make the API really simple. So what did we have? We had a put where every application registers for an application ID, and you provide that with every API. So you have a put that gets the application ID, a key, and a value. And it stores the value against the key. And if you want to retrieve it, you give back your application ID and the key, and you get back the value. So it's a simple key value store or a blob store. Now, where the data gets stored in the background is completely transparent to the user. So on the left top here, the put flows down into a big box which says HBase. That could be 1 cluster, 3 clusters, whatever you want to do in the back end. And you could give quality of service by saying that's my platinum cluster, or that's my test cluster, and that's the cluster where it can go down any point of time and you're just testing on it, right? So on and so forth. So you could actually make this any sort of a cluster, and the application ID would get routed to the right kind of cluster, right? And on the read part, we had a cache because there could be use cases that would read so much that the sheer number of connections could take down HBase. So we had a scalable cache, and we're really good at doing these sort of scalable caches at Facebook. So we just leverage the existing infrastructure. And every read, if it's present in the cache, would just serve the data from the cache. If it's not present in the cache, would fetch it from the store, put it in the cache, and then move on, right, with the answer. So that was the rough architecture. It sounds simple, but there are issues, right? Any multi-tenant solution is not simple. It's never simple. So it was not a self-service model from day one, because we didn't want somebody telling their friend, hey, I used HBase, it worked great for me, and somebody bringing in a use case that's completely not suited for HBase. So we just wanted to make sure that everybody that was putting in data was putting in data for the right use case. So every app was reviewed. So people had to say ahead of time what the use case was, roughly describe what they're doing, how many IOPS, how many reads, how many writes, how much of storage, and so on and so forth. So we wanted to know that ahead of time. Now that's all great. Everybody says something nice in the beginning, but then their use case starts increasing. You got to enforce it. So we actually had per application metrics. So we could track the total number of reads and also break it down per application. So we put that in also from day one, because we really wanted to know who would start abusing, who was a good citizen, who was a bad citizen, and so on and so forth. So that was the second part. One of the things we didn't do in the beginning, but learned pretty quickly, was we didn't put friendly names for the application. So we had like 16-digit numbers, and then you don't know if the 15th digit is different. It's a different application. You don't know who's doing what. So we decided, all the stuff doesn't work when we just put in friendly names. And so it's easier to contact people to fix their own thing. So more of a usability thing, but you live and learn. So if things went wrong, right, if we were able to detect that somebody was abusing their number of reads or writes or just generating too many errors, we could quickly shut off that application and ask that user, at a per application level, we could easily shut it off and ask that user to fix his bug or do what he has to, and or even move him to a sandbox style environment so that he can actually figure out what's going on with his application. So that was a multi-tenant solution. Moving on to the next use case, which is about graph search. The real challenge in this use case, so roughly to give you a motivation for this use case, you upload a photo and tag somebody, your friend in it, your friend got tagged in somebody else's post, your friend got tagged in yet another person's comment, your friend is really popular, so he's getting tagged all over the place. Now somebody comes in and says, hey, show me everything that my friend was tagged in. You got to pull up the photo, the comment, the post, you got to pull up a lot of diverse stuff, and these things have no relation with each other. So we have a lot of diverse sources of data flowing in, and you have to join them every which way, right? And you got to build indexes out of them. So that's what this use case is about. You have multiple independent sources, all of them flow into HBase, and you output, after a lot of data crunching, an image file which is loaded up, or a bunch of image files actually, which are loaded up by the search servers that can actually serve the search query. So the row key is the document ID, like the photo ID or the comment ID or whatever ID you have, and the values are the terms, the actual text in the photo, in the comment, in the album name, the title, the whatever, or the person that got tagged, or the person who liked it, or so on and so forth. So there's a lot of data that gets collected with each piece of, each document, so to speak, in the search parlance. Now, that's how the architecture looks. There's only document source 1 and 2, but usually there's a lot more. So all of these flow into the HBase cluster. And all of this data, when you want to build images, gets pulled into a MapReduce cluster. We actually physically separated the MapReduce cluster to a different cluster and didn't let the MapReduce code run on top of the HBase cluster itself, usually for security reasons. Like you don't want like these applications to take down the core storage and then bad things happen and a lot of people are unhappy. So we usually take the hit of the network latency every time we want to run MapReduce jobs over a critical database, unless it's us writing the MapReduce job, in which case we are responsible, so that's good. And the MapReduce cluster then crunches all the data, joins, does whatever it has to, and outputs a bunch of image files, which are distributed to the search servers, and they load up and serve the queries. Right, so that was a very quick overview of some of the different use cases. I just went for the diversity, like completely different use cases of HBase that we put it to. But at scale, the principles are more or less the same, right? Like the use cases, you got to tune something here, something there, but the overall idea is the same. So what are the overall ideas? First and foremost, you design for failures. Do not design for just a case when like everything is going great and it's sunny and your queries are being served perfectly. But in a distributed system, you will have failures. So 80% on performance and then 20% on some error messages, you got to kind of flip that around. 80% taking care of failures, and then the 20% would be like perform and give your answer. So you can't have a single, so what does that mean? So once you have a lot of machines, some machine will fail, you still have to continue running. That's what we're saying in abstract, right? Because you're going to keep adding machines to scale out. That means you get more and more machines. That means more and more machines will fail because it's a percentage of a larger number which will fail. And so that means you have to not worry about failures. So that means, the first point implies, you cannot have a single point of failure because any machine can fail at any point. Or you should have very few single points of failure, so the probability is still low. But for the vast majority of cases, you cannot have a single point of failure. And so how does that translate into yet another way, right? You can derive from that you can kill any process at any time, and you're fine. You should still keep running, because when a machine dies, your process dies. So just kill any process at any time, continue running. Now, if you can kill any process at any time and continue running, you should also be able to continue running in the face of most common failures. So if you can continue doing that, then you don't need manual intervention for the most common failures, at least all the time. You can do them in bulk and in batch at your convenience, rather than having to do that whenever the thing demands, 3 a.m. or whatever. So once you reach the state where the frequent failures are automated, you don't care about processes and machines dying, of course everything dies, nothing works, right? So within the failure parameters you have set, 10, 20, 30% of failures is okay. After that, nobody can help you. So that's like, you set that up front. And then how does the whole the view change around how you monitor, right? It's no longer about individual failures, it's about uptime, because even when stuff fails, you have stuff up and running. So it's really the uptime that you care about. And once you go after uptime and you can deal with most kinds of failures, then you can actually leverage this sort of a method to do your upgrades. So you just take a node down, upgrade the data, bring it back up, and then voila, you're up and running, right? So rolling upgrades become the norm, and you start thinking in lines of rolling upgrades rather than putting out that maintenance notice, shutting everything down. Those become cumbersome, and generally people appreciate rolling upgrades, as users. Now, one of the things that we realized as we went along this journey with data, with the use case, was that we were trying to march towards a 5 nines availability or uptime, which is like maybe 5 minutes per year of downtime or something really, really small. So that's what we were marching towards. And so at that point, we actually realized that just surviving node failures was not enough. We needed to survive rack failures. So we had to figure out that rack switches reboot, they take about 5 minutes. If it's under 5 minutes, we can keep running and not even do anything. So sometimes you don't react to every single failure. You just hold fort and wait until the rack switch reboots. But if after 5 minutes the rack is not coming back, then hey, you got to do something. So you start this massive split and reshuffle across the cluster and move all your data around and so on and so forth. So we did a lot of stuff to actually get rack failures to become no problem. Like, I'm not going to wake up for a rack failure. But those are unique demands. I mean, I like to point out that you go down this journey and these demands keep popping up, and your own journey will take you down the demands, right? And that's life. So, and that was ours. So, okay, so the next very, very important core piece that I would have to say is the dashboard and metrics. We had a single place that collected everything, metrics from everywhere, right? The one of the systems we talked about, right? But it was presented in the form of a dashboard in a single place. So if somebody says like, hey, something's going wrong with some messaging stuff, you can go in and quickly figure out what's going wrong with what messaging stuff. It's very easy. You can drill down by all the clusters and then go down to the machines and then go down to the exact component, and then you can point out this is what happened, that is what happened, or so on and so forth. And oftentimes it could be like something completely unrelated, like some other process taking over a lot of your network, or the network switch itself not behaving properly, or something completely unrelated. But you should still have the ability to figure out where the issue is and go roundabout in that area and try to drill down deeper and fix it, right? So we put everything in there. Like I said, we would not restrict anybody else. We sure as hell aren't going to restrict ourselves. So we put everything in there, like RPC misses, RPC calls, the total number of calls. So if the application is actually doing more than what they used to do, we could go and say, hey, what's going on? Is this the pattern? Should we really scale for this? Or is this like a bug? Did something happen? So we could actually track and evolve with the application, with the hardware, and so on and so forth. And even for our own efficiency insights, this was pretty useful. So yeah, we had everything, latencies, P99, error requests. We had per request profiling. So those things that would get hidden in the noise but were really bad, we could actually trace them at a small percentage. Cluster and node health, network utilization, everything basically. Okay, the next very useful thing was health checks. So again, a larger fleet of machines forces you to automate your health checking. So it's not possible for you to go to machines and figure out if things are being okay, or if something happens, let me try and figure out which machine is going wrong, or so on. Because every day we had failures. We would have some disks fail, we'd have some machines reboot, and it's just not possible for people to actually respond to these things. Like, I mean, you could, but it'd be a very boring job. So, and a lot of people. So we had to constantly monitor nodes, and our monitoring cannot at any point become so intense that it actually decreases the performance. So we cannot have our monitoring really tied into the live and serving system. The live and serving system would mark something as down if it is slow, but that thing can reboot and come back and join, and it should just work, right? That's the live serving system. But the monitoring system will come at a later point of time and try to figure out, is the disk okay? Is the memory okay? Is the network okay? Am I able to SSH to that machine? Is something going on? So, and so on and so forth. So the monitoring system is completely decoupled from the serving system and would come in at its own sweet pace and try to mark something offline in an automated fashion. So it'd come and say, hey, disks are bad, let me mark that offline. It's like, let me mark that as to be repaired. Or the machine is bad, let me mark that machine to be repaired, or so on and so forth. And then a technician could come after his own, get up in the morning, have the latte, whatever, come into work, and okay, these are the disks I gotta fix all that stuff. and not have to be woken up and have to fix it right now. Otherwise, man, what's this? There are users that are suffering. Like, that's not the mentality ever. So automatically exclude nodes and then fix them whenever you want. And then the guy goes and fixes all of the issues, and then he marks all of that stuff good, and then it gets automatically included back. Because again, adding it back into the cluster, man, that's another boring job, right? So, and one of the things we did was really rate limit the number of machines we add at any given point in time. We don't add too many machines. The system is built to scale out, but not scale out by adding like tons and tons of machines. Like, you can't have more machines than queries being added, right? I mean, that just doesn't make sense. So we can add at a rate limited fashion because you want to minimize churn on a running cluster. So rate limit the remediation of nodes, whether it goes out or in. And by the way, too much of intelligence is also a bad thing. So if your automated system is trying to mark like 80% of all your nodes offline, it's probably something going on. So we actually had limits saying don't do anything if you're going to mark more than this percentage in a day offline. So, and at that point, do wake somebody up. It's okay, So, okay. So actually, a lot of stuff was around waking up at 3 a.m. It's not fun. Yeah. So rack failure is don't exclude rack failure. Yeah, so our automated system would actually mark nodes offline, but it would never mark a whole rack offline. So if too many nodes failed, it would just back off. But what our system did internally was, if a rack was failing for, say, under 5 minutes or 10 minutes, it would do nothing. It would just let the failures be visible to the user. Like, the user would get some sort of an error message, but it would not service the reads or writes. But after 10 minutes, it's going to automatically move all the shards and all of that processes on that rack. It'll declare that rack dead in software, and the running system would start serving it from the remaining machines. So suppose you had 100 machines, right? It was one of our typical examples. A rack was 20 machines. So that's about 20% of your serving cluster. If that rack is deemed dead, you're serving your data out of your 80%. But we would never mark all those 20 machines as put them in repair. Some technician has to look at them. So that would be a little too bad, because nobody would look at it the following morning, and then that would go into repair, and you just don't know what happened. So we don't do that much of intelligence on the health checks, but on the online system, oh hell yeah, it has to serve, right? So after 10 minutes, it'll automatically move and the reason for this 10 minutes thing is an artificial thing. You can make it a couple of minutes, but the problem is, if a rack switch reboots, it takes like, say, 3 minutes, right? You've now moved 20% of your shards out, and then that thing comes back, and now you have to move 20% of your shards back, and that's like a lot of stress, and the cluster is not going to be very stable during that time. So we're okay with some failure. We're just not okay with a lot of failure. So, all right. So, okay. So in a nutshell, right, summarizing everything, we use commodity hardware because it keeps costs down. We're going to scale out like hell, so just keep the cost down. And scaling out is number one. So always make sure you're able to scale out, and then make sure you're very efficient within the architecture for scale out. If you go the other way and lose out on scale out, you'll get great efficiency, but you may not be able to manage it. You may not be able to keep up with the growth. So scaling out is number one, and efficiency is number two. But that number two is not really very far from the number one, because if you keep adding machines, it's better be efficient. So efficiency is close behind scaling out. It's not like, let me just forget about it. So, and then design for failures. Failures is not an afterthought, a band-aid on top of an existing system. That's usually much harder to do. It's much easier to build it from within and have the system understand failure and be resilient to failures, and definitely be resilient to frequent failures. Otherwise, boring job, lots of people, And finally, have a lot of metrics. Make sure that you're able to figure out where the issue is, like see the smoke and then go find the fire, because it may be so big you may not be able to find the fire. So, all right. So so that was all about some principles, whatever that we did at Facebook based on big data, right? So let me now go over, like at Nutanix, what is it in these principles that we do, right? So I just cut and pasted a bunch of points that was there on the why did we choose HBase slide. And obviously the first one's not important because Nutanix is a storage system, so let's skip that. Horizontal scalability. So extremely important, because as your workload, so we're in an age of data explosion, right? Like it or not, more data is going to come in. 5, 10 years ago, very little data, a lot more data. 5, 10 years from now, a heck of a lot more data. So adding nodes, coming up to this, it's going to work to a certain point, but after a certain point, the data is going to get unmanageable. So make sure that you're able to scale out for that data, right? Don't have any inherent bottlenecks in the architecture. So Nutanix is built with scale out in mind, and automatic failover and load balancing. So once you've bought into the first premise, you need scalability. You're going to have a lot of machines. You're going to have a lot of failures because it's a probability multiplied by a large number. It's going to be a bigger number of failures. So it's got to be able to be resilient without being a bottleneck. Like you need some sort of load balancing, and that principle is also built into Nutanix because, and by the way, a lot of what I'm going to say is going to sound similar, and it's not because it's kind of morphed to be that way. It's because like people from Google and Facebook are the people involved with Nutanix, and any of Google, Facebook, Amazon, you take any of the big guys, they're going to follow similar principles because it's just what works at scale. Like it's just not possible to work it any other way. So okay, HBase was optimized for write-heavy workloads because at Facebook we have the luxury of optimizing our storage around our really large applications, and the large applications are really, really large. They go into petabytes, so it's worth the engineering time and the effort and the DevOps time and effort to come up with this solution, implement, keep it up and running, and so on and so forth. But at Nutanix, we're serving the needs across a wide variety of customers, so it may make sense at the multi-petabyte scale, but at the terabyte scale, it may not make sense for everybody to go and hire a team and then build a solution and then keep it up and running. It just doesn't make sense. So, but if you take the aggregate across all the customers that face this problem, that sum does add up to a sizable number. So it does still make sense to bring those principles across the cross-section, right? And which is what Nutanix is all about. So what we are optimized for is a virtual environment because you can run virtually anything in there. So we are optimized for virtual environments, and we are more or less optimized for read and write workloads, and that's by using flash. So we absorb all of the random writes, really bursty random writes, and really random reads on the flash tier, and then trickle down to disk. And we do management of hot data and cold data across flash and disk. And another interesting thing is the transparent use of flash itself based on predictive I/O. Like it does some predictive I/O. Like if you read something, it brings the hot stuff onto flash and so on and so forth. And that's really good for legacy applications because flash and disk are really very different beasts. They have very different characteristics. And if used properly, flash can give you a lot of good performance. But the legacy applications are mostly agnostic to these newer technologies. They don't know about flash. They don't know how to use flash. They either know to write on a media or not. And that media was designed to be disk. So Nutanix will help you transparently use flash in a more efficient way in a legacy application. HDFS being battle tested at Facebook was a big comfort to us. So Nutanix is also quite battle tested. We have over 300 customers. So it's been put through quite a bit of rigor. And HBase has a strong consistency model which allows a wide variety of applications to run on top of it. Similarly with Nutanix, it's also a strong consistency model. So let me just go into the other aspects of the Nutanix solution, right? So it is architected for failures and for manageability, right? At Facebook, we built a lot of custom solutions, and clearly that's not very practical if each person has to go and build their own custom solution for managing. So it comes with a nice UI, a Prism UI, which gives you, so the software automatically for the live serving part marks nodes as offline, marks disks as bad, and so on and so forth. And in the UI, it also pops up an alert, which is actionable, which tells you what went wrong with the system. So you'd be able to leverage that. And similarly, it also gives you analytics into what's going on in your cluster, how many IOPS, what are the number of reads, writes, whatever you want into the cluster. So you'd be able to get an idea of what is going on, the storage space used, or what have you. And yeah, uptime is important. So like we said, rolling upgrades become the norm. So in Nutanix, we do rolling upgrades. So we just take one node down, upgrade the software, bring it back up, and move on. The need to survive rack failures is not done because we didn't need to do it. We didn't face it. But the key takeaway there is that different use cases and different scale of use cases will bring different challenges, and we will adapt to stay relevant. So we will put in the required thing. And it makes sense for us because across all the use cases, like whatever we're focusing on as a business, it does make sense for us to do. Yeah, we do have a single play. I think the Prism UI covered it out of order. And yes, we do constantly monitor nodes and mark them offline, which we also talked about. So in a nutshell, the core principles, like if you were to summarize everything, it does run on commodity hardware, and it is built with a scale-out first in mind. And efficiency is a constant thing in progress, different use cases, constantly different types of hardware, different types of flash, different densities of disk. So efficiency is constantly being worked on. And then you design for failures. So if something fails, it should continue running, and it will tell you what failed so you can replace it and eventually bring your cluster back to the right state. And finally, metrics. So we do have a fair good amount of metrics in the UI in a very usable fashion. So I think that's about all that I had. So if you guys have any questions, yeah. Thank you. Yeah, go ahead.
Are you still working for Facebook, or have you?
No, I started working for NUTANIX since this April, so I'm a member of technical staff at NUTANIX right now.
Because I'm thinking of what could be more interesting, challenging environment that the end customer in Facebook therefore to move from end customer to a provider. And what is
No, actually, I have always been a provider. At Facebook, I was a service provider, infrastructure provider for other applications and products and other things in Facebook, because the end business of Facebook is a product, right? It doesn't sell service, right? But at NUTANIX, I'm also a provider, but for other end customers who are users, right? Like you guys, so. Questions? Good? Awesome, great. Thank you guys.
So no, you can switch. Gut, ich brauche etwas Vorbereitungszeit. Mir hat jemand den PC abgeschossen. Ja, leider ist er nicht multinode-fähig wie NUTANIX. Da habe ich jetzt die Strafe dafür. Falls einzelne Leute schon gehen müssen, weil es schon fortgeschrittene Zeit ist, bitte ich euch einfach, die Beurteilungen auszufüllen. Es hat noch eine Checkbox. Ich bin an mehr Informationen über NUTANIX interessiert. So werdet ihr dann mit zusätzlichen Informationen beliefert. Dann noch ganz kurz, ich weiß nicht, ob es eingangs erwähnt wurde, hier wird ja gefilmt. Das wird auf YouTube entsprechend veröffentlicht. Wir können also alles nochmal nachschauen. Müssen in dem Fall nicht unbedingt nur Präsentationen verschickt werden. Kannst du etwas dazu sagen, Oli, als Regisseur? Wann ist das oben?
Wahrscheinlich heute Abend schon oben, aber dann wird der Link morgen oder übermorgen.
Ja, der wird automatisch dann verschickt über Digicomp. Ja, so seid ihr dann entsprechend informiert. Was?
Da konnte mir das Bild auch mit abfilmen wie Live-Demo.
Aha.
Die Netze sind klein für Windows. Da musst du ausführen.
Ja. Vielleicht ist zwar Copyrighted Content, also sollte einfach.
Das musst du sagen.
Ja, sonst ist nicht einfach so, dann ist nicht so klar, weißt du, sonst kannst du Buch 1 zu 1 anders. Jetzt das Buchkapitel.
Also die ganze Kapitel auf dich. Das ist eine Live-Demo-Sache.
Genau. Irgendjemand hat mir leider den PC terminiert. So.
Sollen wir sie noch kurz ins Datacenter schicken?
Ich komme gerade drauf, weil ich bin jetzt gerade so weit. Ja. So, da bin ich schon praktisch soweit, habe recovered. Ich möchte 2, 3 Worte sagen noch zu VMware Fast Track Infrastrukturen. Das ist auch der Grund, wieso ich dann schlussendlich wirklich Berührung hatte mit Nutanix. Ich habe untersucht in einem Buchkapitel von einem Buch, das nächstens erscheinen wird über View, Horizon View, wie werden heutige Infrastrukturen, vor allem für Desktop-Virtualisierung, gebraucht oder entsprechend gebaut. Da habt ihr entsprechend spezielle Anforderungen. Die Skalierung zum Beispiel pro Arbeitsplatz, der Preis ist da sehr, sehr wichtig. Wenn ich eine traditionelle Infrastruktur nehme und dann langsam wachse, kann es sein, dass mir die Kosten natürlich aus dem Ruder laufen. Und die Entscheidungsträger, die haben natürlich sehr genaue Vorstellungen, was ein Arbeitsplatz kosten darf. Das habt ihr in der normalen Virtualisierung eigentlich nicht so wirklich, oder? Was ein Server kostet im Betrieb. Ein Exchange-Server, der kostet halt einfach irgendwie. Man vergleicht verschiedene Hersteller, verschiedene Server, verschiedene Storage-Systeme, die man am Ende zusammenbaut und hat dann irgendeinen Preis für diese Infrastruktur. Die einzige Messgröße, die sich heute eigentlich ergibt für ein Postfach, ist, wenn ich einen externen Provider nehme, der Hosted Exchange zum Beispiel macht, kann ich natürlich sagen, eine Mailbox würde so viel kosten beim externen, also die interne IT darf da für diese Applikation oder Service nicht teurer sein. Beim vSphere Fast-Track-Programm, da geht es darum, günstige Lösungen zu bauen. Ich gehe hier gleich mal auf das Fast-Track-Programm. Das ist im Prinzip das Buchkapitel. Ich erwarte jetzt natürlich nicht, dass ihr das so schnell durchlest. Ich nehme hier nur ein paar Punkte raus. Und da seht ihr entsprechend, steht natürlich auch schon Tipps for Low-Cost VDI, weil es geht beim Arbeitsplatz natürlich um tiefe Kosten. Wenn ihr heute einen PC kauft, der ja alles drin hat und ein OS drauf, dann kriegt ihr eine anständige Maschine für 1000 Franken, sage ich mal. Und habt entsprechend schon OS drauf. Und ich kann natürlich nicht mit einem Arbeitsplatz kommen, der hinten ein super Storage-System hat und schöne Server vorne dran etc. Und am Ende kostet mich dieser Arbeitsplatz 2000 Franken. Das kann ich vielleicht bei Servern machen und Server-Services, aber nicht bei einem PC-Arbeitsplatz, da weiß jeder, was das kostet. Und erschwerend in Zukunft natürlich bei einer VDI-Lösung, dass ihr entsprechend nebst der Hardware eine spezielle Softwarelösung braucht. Ihr braucht ja nicht nur die Hardware und das OS, ihr braucht ja auch noch vom Hersteller diesen Connection Server oder was immer dahinter ist, diese Software muss auch noch bezahlt werden. Und dementsprechend sollte der Preis trotzdem irgendwo bei 1000 Franken bleiben. Das heißt, darum ist natürlich auch einem Hersteller wie VMware bewusst, wenn ich etwas machen will, brauche ich da Low Cost, damit die Preise nicht aus dem Ruder laufen. Als ich das Buch geschrieben habe, habe ich mich natürlich damit beschäftigt und ihr seht hier natürlich verschiedene Hersteller, die entsprechend hier kommen. Ja. Die alle machen irgendetwas mit VDI, sagen, ihre Lösungen sind für VDI, zum Teil ist es auch nur ein Fragment. Also Fusion.io macht eigentlich ja nur Flash Storage. Damit kann ich einen Part entsprechend beschleunigen. Und ich habe mir all diese Hersteller mal angeguckt und ihr Konzept und muss sagen, NUTANIX ist absolut das, was beeindruckend war für mich. Es ist eine Lösung, die voll integriert ist, entsprechend Scale-out-fähig ist. Ich kann mit etwas ganz Kleinem starten, mit 3 Nodes, das ist das Minimum, dass ich ein Cluster habe, der redundant ist, und habe nachher alle Möglichkeiten zu wachsen. Ich kann sagen, ein Node hat 100 User, die supported werden, brauche weitere 100, schiebe ich wieder einen Node hinein. Wenn dann halt 4 Nodes in einem Gehäuse sind, muss ich ein neues Gehäuse kaufen, mit einem Node, integriere den in den Cluster und ich skaliere. Es ist eine richtige Scale-out-Lösung und da unterscheidet sich das Konzept von entsprechend vielen anderen. Mittlerweile konnte ich auch natürlich mit vielen Leuten sprechen, wie sie denn das sehen würden in ihrem Betrieb und haben natürlich gemerkt, das kommt sehr unterschiedlich an. Es gibt Leute, die sagen, ja, das alte, Anführungszeichen, das kenne ich weiß, es funktioniert. Und was ich gemerkt habe, ist, der Wille eigentlich für so eine Scale-out-Lösung ist sehr groß, aber es kommen dann natürlich viele politische Fragen. Ach, wir haben ein Storage-Team, aha, die müssen jetzt einfach diese Harddisks der Node verwalten oder wie läuft das? Das Problem ist natürlich, solche Architekturen, die wirklich einen Umbruch darstellen in der Produktion, in der IT-Produktion, bedingen auch, dass ich mich organisatorisch entsprechend etwas anpassen kann, dass halt das Ganze integrativ ist. Aber das ist unsere Zeit, mit der Virtualisierung hat das begonnen. Ich muss etwas wissen über Storage, über Netzwerk, über Server, über die Virtualisierungslösung, über die Gäste. Ich kann nicht mehr den Silo denken, vielfach, wo ich einfach sage, ich bin nur für Storage zuständig, alles andere geht mich nichts an. Ja, das werden wir wahrscheinlich viel, viel weniger erfahren. Dann vielleicht, was auch noch ein Unterschied ist, einfach technisch zur Servervirtualisierung. Das habe ich hier mal aufgeschrieben, ein paar Punkte, wo eben NUTANIX effektiv absolut gut punktet. Ich habe es ausprobiert, wir haben ja da eine entsprechende Hardware. Für diejenigen übrigens, die das noch sehen möchten, physisch, ich würde dann, nachdem wir hier beendet haben, den Vortrag, die Möglichkeit geben, ins RZ zu gehen und dann könnt ihr es auch mal physisch sehen, welche Anschlüsse da sind. Ich kann es auch kurz dann erklären, oder wir haben natürlich hier ja auch die Leute von NUTANIX, die das können. Ein großer Unterschied zu Serverinfrastrukturen sind Bootstorms, die ihr entsprechend habt bei vielen virtuellen Desktops, wenn ihr euch entscheidet, zum Beispiel die Desktops auszuschalten über Nacht, um entsprechend Power Savings zu betreiben. Und morgen kommen alle Leute begeistert an die Arbeit und wenn dann viele Arbeitsplätze hochgehen, hier skaliert das einfach sehr gut, weil es über Node verteilt ist, die immer zugeordneten Storage haben. Dann natürlich Login-Storms, eben auch das. Leute gehen hin, loggen sich ein, User-Profile werden geladen. Das sind alles Sachen, die wir in der Server-Virtualisierung so nicht haben, ja, die effektiv von den Clients herkommen. Und dann haben wir natürlich auch da die Benutzerdaten oder Linked-Clones. Also ihr seht verschiedene Typen von Daten, Sachen, die nur gelesen werden müssen, Sachen, die aber auch geschrieben werden müssen. Und die Lösung ist wirklich sehr, sehr gut skalierbar, wie ich feststellen konnte. Es gibt nicht etwas, das dann da irgendwie einbricht. Es ist ein wirkliches Scale-out-System. Ich hoffe, euch hat die Veranstaltung gefallen und war etwas Neues, Interessantes in der Datacenter Night-Serie. Und mich würde es natürlich entsprechend freuen, wenn wir bei anderer Gelegenheit uns wiedersehen. Ich stehe selbstverständlich noch für Fragen zur Verfügung und wie gesagt, diejenigen, die noch den Blog richtig berühren möchten, ja, die haben nachher noch die Gelegenheit. Danke vielmals für die Aufmerksamkeit und bis ein anderes Mal.